Good morning and welcome to the Kennedy Space Center for this aeronautics research update. The first A in NASA stands for aeronautics, so it's particularly fitting that the Aeronautics Research Mission Directorate should kick off this day of briefings on NASA's upcoming activities. With me on the panel today are Ed Waggoner, who is the Director of the Integrated Systems Program Office at NASA headquarters in Washington, and John Cavolowsky, who is Director of the Airspace Systems Program Office at NASA headquarters in Washington. And they're going to talk to you a little bit today about how NASA is working to make air travel safer, greener, and more efficient for you, the flying public. Ed?
Yeah, we'd like to start off the aeronautics part of the What's Next discussion just with a few economic factoids that help explain why NASA is working in aeronautics. As you know, aviation touches most of the general public and the taxpayers. It has a huge impact on our economy. Aviation manufacturing and associated services are a powerful economic generator. As a matter of fact, it reduces the country's negative trade balance by about 8%. 1/4 of all U.S. companies' sales depend on air transportation. The aviation industry provides 500,000 manufacturing jobs and another 165,000 transportation service jobs. And these jobs support over 150 domestic airlines that are flying over 8,000 aircraft, transporting around 2 million passengers a day. These airlines bring in a combined operating revenues of over $140 billion a year. So you can see it's a powerful economic force for the nation. Now, for the past several years, NASA Aeronautics has been given some very powerful national level guidance, starting with the National Aeronautics R&D Policy, which was published in 2006. This dictated that a National Aeronautics R&D plan be developed, and that the first generation of that plan was developed or published in December 2007. That was followed with an update to that plan in February of 2010. These documents establish 6 basic tenets for aeronautics R&D, mobility through the air being of vital importance to the economic stability, growth, and security as a nation, assuring energy availability and efficiency, making sure that the environment is protected while sustaining growth in aviation, and maintaining aviation safety, that's paramount to the work that's done. And then aviation is also vital to the national security and homeland defense. And then the 6th tenet is making sure that we have world-class facilities that are available to support the work that needs to be done for aeronautics R&D. In addition to the aeronautics R&D plan and the policy, the Vision 100 legislation, the Century of Aviation Act of 2003, was established the Joint Planning and Development Office and charged that office with developing a plan for the next generation air transportation system, and John will be describing that later during his part of the presentation. And then in August of 2007, the Joint Planning and Development Office published what they call the Integrated Work Plan, which is essentially a roadmap from where we are today to the next generation air transportation system in 2025. And this included a detailed research and development plan. Now, the first slide that we have this morning shows how NASA Aeronautics Program focuses on conducting research in support of next-gen safety, energy and efficiency, and reducing the environmental impact. And this work is organized around 5 areas of research. Aero's largest research area is focused on a broad suite of vehicles, fixed-wing vehicles that fly from subsonic through transonic through supersonic speeds, focusing on efficiency, emissions, fuel consumption, increased mobility through the air for faster transportation, and in the case of supersonic vehicles, in reducing the sonic boom or making sonic boom more acceptable. In this area, we also do work in rotorcraft. Just think helicopters and the way helicopters can fit into the air transportation system by having helicopters with increased speed, range, and payload while decreasing noise and emissions associated with them. And then hypersonic vehicles. And this enables air-breathing access to space, high-mass entry, descent, and landing into all planetary atmospheres. The second area is research in air traffic management. This is focused on developing and demonstrating concepts, technologies, capabilities that enable any air traffic service provider, in our case for the U.S. it's the FAA, to provide major increases in air traffic management effectiveness, flexibility, and efficiency in our system. And John will be discussing this a little later as well. The third area, we conduct cutting-edge research into safety. This produces tools, methodologies, concepts, various technologies to improve the safety attributes of current and future aircraft and overcome some of the safety barriers that would otherwise constrain the realization of the next generation air transportation system. The newest area of research is focused on integrated systems, and we're conducting this research on promising concepts and technologies, demonstrating those benefits in a relevant testing environment. We have two primary projects in that area right now. The first one we'll be talking about today, environmentally responsible aviation, and the second one has to do with integrating unmanned aircraft systems into the national airspace system, looking at capabilities that reduce the technical barriers to do that, to be able to safely operate unmanned aircraft in the national airspace system. And then all of this research is built on a foundation of both ground and flight test facilities. NASA manages these testing assets to ensure the relevance and the viability of the testing capability to meet the United States aero industry needs. So recent augmentations to the aero budget was a clear signal that Congress values aeronautics and the work that we do in R&D. In 2010, we got a permanent increase of around $60 million that allowed us to launch the Integrated Systems Research Program. And then this year, we got an additional $30 million for new efforts that include getting the UAS and the NAS project started, verification and validation of complex systems that's being worked out of the safety program, and some additional funding for our innovative concepts in aviation work. Our budget in 2011 was $533 million. That supports the research of 1,370-ish civil servants that are doing the work of aeronautics. And these are primarily housed at 4 NASA centers: Ames Research Center in Mountain View, California, which is just south of San Francisco; Dryden Flight Research Center, which is adjacent to Edwards Air Force Base east of Los Angeles; Glenn Research Center in Cleveland; Langley Research Center in Hampton, Virginia, which is in the southeastern part of Virginia. So how do we accomplish this work? The strategy of our investments is really we take a 3-pronged approach. We start with the ideation process, or what I call the ideation process. And there's where we're taking just ideas that often researchers have from observations that have been made or what they think might work. We fund this work either within the programs that we have, or we have a way to actually fund this outside the programs where the ideas may not fit directly in a program in their most embryonic stage. Then this work is matured through our fundamental technology programs, and then the more promising concepts are actually worked further in the Integrated Systems Research Program. And in all of this, we're dedicated to technology transfer, and that is to various stakeholders, which include industry and other government agencies. And this ensures that the U.S. taxpayer gets the most bang for their buck in the investment in the aeronautics work that we do. We feel that this strategy enables game-changing concepts and technologies that are derived from advancing fundamental research that ultimately leads to understanding the feasibility of advanced aircraft systems, the total systems. And we know that we can't do this alone. So we do work. We work closely with U.S. industry, with other government agencies, with academia, and international collaborations as well. We've been strengthening our relationship with industry at the peer-to-peer level for several years. And this year we're focusing on strengthening our relationship at the senior executive level. And an example of this is the Aeronautics-sponsored industry roundtable that we'll be kicking off later this year. And in addition to this, we've been working to develop international partnerships in areas where each party has some capability or assets that is mutually beneficial to the other. So after some introductory remarks, John's going to narrate a short video that further describes some of the challenges and the research that we're doing to address those challenges. So John?
Good, Ed, thanks. Good morning, and I'm very pleased to have this opportunity to spend a few minutes talking with you about what's next for NASA Aeronautics and to describe how we're working with the aviation community to address the challenges of creating the next generation air transportation system, or NextGen, as Ed had introduced to you just a few minutes ago. Now, chances are those of you here didn't fly to this site today. You didn't have a personal interaction with the air transportation system. But I expect that you very likely enjoyed some fresh fruit over the last day that was not locally in season. You may have ordered your new 4G smartphone and had it arrive that next afternoon on your doorstep. And you also could have sent some critical overnight package that absolutely, positively needed to be at that customer meeting the next day, and it was. Now, these and many other what we now consider everyday expectations are only made possible by a safe, reliable, robust air transportation system. And frankly, these are all expectations that 30 years ago we couldn't have had to the same degree. What will that demand? What will our expectations be 30 years from now? Though this is the essential question that we're asking, and that we're working to answer in aeronautics at NASA. So what I'd like to do now is set some context for today's air travel, the way we interact with it, and provide some suggestions for what that 30-year future may look like. So could we please kick off the video? Now, aviation is a global enterprise. It's a very complex network. Again, covers the many nations that we interact with, we trade with. But the complexity is greatest here in the U.S. We manage the largest airspace in the world, and it's growing, perhaps doubling over the next 20 years. So what you're watching here is an animation of a day in the life of our air transportation system, and it's displayed using FACET. It's a Future Air Transportation Management, or ATM, concept evaluation tool. You can see the outline of the U.S. in red, blue are the sectors managed by the FAA. 24-hour clock in the lower right, starting around midnight, shows the time of day, and those are real flights. Again, this is a day in the life. About 5,000 aircraft are in the sky at peak times of the day. You can see kind of the tail end of the red-eye traffic coming in from the West Coast, East Coast heating up. You saw perhaps the cargo hubs, Memphis and Louisville, getting busy early in the day. International flights are beginning to arrive as well as depart. You see on the East Coast. And the East Coast hubs certainly have woken up, and transportation is busily creating economic benefit across the nation. The rest of the country follows suit finally with the West Coast providing that benefit. Now you'll see some spots that aren't fully utilized. Frankly, there's special use airspace that we have to manage around. You see a couple triangles in the southwest corner of the U.S. associated with military controlled airspace. And air traffic management manages the interaction of these complex flight patterns, very structured airspace with rigid waypoints. And actually this is all fine while the weather's good, but as the day was indicating, but somehow weather tends to get in the way often of our efficiencies. And here we show a shot of the Northeast Corridor with a severe weather pattern settling in over New York. No longer are those blue tracks heading into the New York area able to efficiently make it into the city and the cluster of airports, the Metroplex, but many holding patterns and inefficiencies are placed in that. 70% of the delays in our system today are due to weather. Currently, controllers talk directly to airplanes and pilots to reduce these delays and reroute traffic around these hazards. But as we look at NextGen, we need better tools to predict weather and impact that. We need to save fuel. Arrival paths, runways are managed largely by this stair-stepping or dive and drive flight to touchdown that you see. It's waste fuel. We need to develop capabilities that allow smooth, continuous descents to the airplane surface. To the airport surfaces. Plus, managing movement of the aircraft on the airport surface and other inefficiencies are rampant. We can gain some. Many of you have been stuck in 20-minute, 30-minute, 60-minute conga lines, missing your connecting flights. Leads to waste of time and fuel, and emissions and noise for neighborhoods or on airports. We need to be planning our gate departures for non-stop taxiing and smoother operations. But again, as we look towards this future, it's not all about the operations. What are those new aircraft designs that will enable greater mobility and opportunity for the nation, new business models? We can look at novel approaches to subsonic flight. Supersonic aircraft can provide even greater efficiencies, and hypersonic considerations no less. But we also need to look at innovating our current operations and current aircraft to get the best use that we can, the greatest efficiency out of our current configuration. And we have to ask our question, can innovation allow us to utilize our existing airports and infrastructure for greater benefit? Civil tiltrotor shows potential for just this, and we need NextGen to be able to manage these operations for all these different aircraft with their different performance and business objectives, all flying safely and flying efficiently. So to kind of put a wrap on this video, NASA Aeronautics is addressing the great challenges of transition to NextGen. We're partnering with some of the best innovators both inside and outside of government, and we will lead this global change to meet the demands of mobility, both now and in the future. But achieving this future requires that we step up to many technical challenges. So what I want to do now is start a new segment where I take a few minutes to talk to you about what's next for NASA Aeronautics research, specifically in areas of air traffic management. So if we could go to the briefing slide package, please. So my hope is that I provide a little bit of clarity that air traffic management plays a big role in solving aviation challenges. But what exactly are air traffic management tools, and in fact, what is NextGen? So first, let me explain. NextGen is an effort, a multi-agency, nationwide, government initiative that's designed to transform our current air traffic control system. That current system is a radar-based surveillance and radio voice communication system, very similar to that which was put in place back in the 1950s. Current system cannot process and cannot provide the flight information in real time, and current flight procedures don't allow for agility needed in order to meet the growing and dynamic demand that we see our air transportation requiring, our needs and our economy requiring. And this current system is expected to be replaced by satellite-based surveillance with network-enabled information and data sharing that will allow greater precision in aircraft position and a common awareness of all flights in the system. Now, NASA Aeronautics conducts research and develops technology that makes use of this data for thousands of aircraft that are in the air at a given time that require efficient operations and flows. It does a computational analysis, in essence, of all that data in order to provide sequence of these fleets of aircraft for most efficient system operation and ultimately reducing delay for the flying public. Our technology provides more efficient approaches to manage traffic flow, and it provides options to controllers and airline operations in order to support their decisions on how best to control the skies and to control their airlines. In many respects, NextGen is about the users. It's about their operational needs, and our tools with the improvements to the NextGen infrastructure are designed to provide that. Now again, our research investigates gate-to-gate solutions. So in other words, from our departure gate through the dense metroplex terminal airspace into the en route airspace and to final approach and landing and efficient taxis to our arrival gate. This work clearly, for sure, supports the FAA mission in air transportation management, but it also supports the needs of airline operators and their carriers. Our technology solutions examine not only those solutions that are implemented at the centralized ground-based FAA control centers, but also implemented through automation available in increasing degrees on the actual flight deck, on the aircraft themselves. This range of control technologies offers opportunity for system scalability, not currently available in our fixed ground-based infrastructure of today. And frankly, the overarching goal is to create decision support tools that simultaneously save time and reduce aircraft fuel use, reduce noise, and reduce emissions. So if we can go to the next slide, please. This is just an example, a straightforward graphic of benefits from such optimization of flow paths. Coordinated arrival trajectories that can enable delay-reducing, fuel-conserving, and noise-mitigating operations. Here you see some actual flight paths with some new procedures that we had helped develop in conjunction with the FAA over the San Francisco Bay Area. Flights coming into the airport at San Francisco significantly, and you can, without understanding the specific levels of reduction, it's clear to see that the noise due to proper and efficient operations and management of these flight tracks are reducing noise over neighborhoods, centering out over the bay, which clearly mitigates some of the concern that many of those neighborhoods have had for years regarding those flow paths. If we go to the next slide, please. But what I really would like to talk to you about today more specifically is a near-term air transportation management technology demonstration activity that we're initiating, and we're initiating it now. It's an optimizing arrival of aircraft demonstration, which is an aggressive technology acceleration and demonstration activity that's going to integrate several research components to safely sustain peak throughput and provide fuel-efficient operations with improved aircraft separation. We need to bring together multiple capabilities, both on the ground, again, the ground-based control tools, and airborne tools needed to efficiently achieve and maintain spacing and reduce delay. And the critical challenge will be to achieve these operational and environmental benefits simultaneously. Again, efficient ops, spacing, and efficient and fuel descents. Again, do that all simultaneously, but the key point, at congested airports. Many of the capabilities that are incorporated into this collections, integration of technologies and demonstration are available one-off. We can have smooth, efficient descents. We can do it at times, however, that aren't congested or non-busy airports. The key to many of our needs for the future are going to be taking these technologies and being able to put them together to achieve all of these benefits when the densities are high and the traffic demand is high. If we go to the next slide, please. So optimizing aircraft arrivals is going to further develop, test, and validate tools for use at congested airports to reduce controller workload and provide these numerous benefits. The NASA-developed technologies that we're going to be integrating for these optimal arrival solutions are including advanced traffic management scheduler, where we're actually managing flows that are in this dense terminal area. We've been working with the FAA for a number of years to bring capabilities that begin the process of managing and organizing flows for efficient arrivals at distances farther out. But the key to being able to do this well is to be able to manage these flows and provide these efficient operations in the dense terminal environment. And also to take advantage of a capability we refer to as flight deck interval management, which is a technology, automated technology on the flight deck of aircraft that can allow the aircraft to manage a very precise and efficient arrival path to the runway threshold, employing a capability referred to as ADS-B. And I'll take a moment in a short while to explain what that cryptic acronym is. But benefits for this approach are going to include reduced flight delays, reduced fuel use and workload on both pilots and controllers, allowing higher traffic flows that can meet the increasing demand, reducing implementation risk for partners. And what I mean by that is our job at NASA is eliminating, to the greatest extent, unknowns, to establishing clear requirements and defining benefits case. These are the precise things that both our federal partners, the FAA, and industry needs to understand whether they have the opportunity to apply and to provide benefit from these capabilities and these new technologies. We increase the technology readiness, if you will, the maturity of these through these series of demos, hence reducing their risk to taking that capability and bringing it to the field. We're also accelerating development of air traffic management tools that enable the overall next-gen objectives, but specifically accelerating the development of applications that provide the full benefit of ADS-B equipage. Now, ADS-B is Automatic Dependent Surveillance Broadcast. It's a crucial component of next-gen and is a satellite-based system that allows both pilots and controllers to see radar-like displays of traffic and update that in next to real time. We talked about the radar-based control that we currently operate in. Aircraft position is updated every 11 to 12 seconds. This, at nearly full time, every second update provides for much more precise measurement of exactly where traffic is and how we can better plan those trajectories in order to keep them safely separated. It also gives pilots access to better weather information. It's more than just position and velocity, and also other elements of flight information. ADS-B is going to allow greater responsibility for safe separation to be managed by the pilot, reducing some of the workload for the controllers, but also providing that much greater precision in terms of the position of that aircraft to be able to save time and land more aircraft with higher throughput. So NASA is developing the applications to analyze this data provided by ADS-B infrastructure and to provide to pilots and controllers these safe and fuel-efficient routes with a minimum delay. Could go to our last slide, please. And as with all technology solutions, for transition to users and operators and implementation in the NAS, these problems are big and they're complex, and they require collaboration across multiple organizations, both inside and outside of government. Now, the FAA is a critical partner with whom we have worked very closely over a number of years, but most closely over the period that I was talking about since our national planning efforts. To align our missions across our agencies and our objectives, and in striving to make true operational impact. Our bottom line goal at NASA and aeronautics is to make a difference, make an impact with our investment in aeronautics infrastructure and research. But we're striving to make that operational impact and delivering accelerated and aggressive schedule for these particular demonstration capabilities and the benefits that I listed on the last slide. We're setting this up in roughly a 3-year horizon, where we're developing and testing some of our basic technologies and tools and algorithms. A lot of that will be done at NASA centers. In the second year or middle part of this demonstration time frame, we're going to be evaluating further the benefits and the operational improvement of these technologies that we've integrated through some very sophisticated simulations, a number of which will include human in the loop. We bring in real pilots, active controllers to interact with our technology and our substantial simulator capabilities that will allow us to understand how they interact in some of the true human-machine interactions that are often limiting factors in how well the technology is accepted and implemented. And then finally, as we go forward in the last year of this, we're going to be conducting field tests with partners at real congested airports and terminal areas. So this addresses the need to meet a time frame that provides real benefit for actual users in the relevant operational environment. Now, we don't implement these improvements in the NAS. That's the responsibility of the FAA. But we will deliver the requirements, we'll deliver the tools and the validation test data to allow them to accelerate this operational deployment, again, for that national benefit and to enable the economic activity and the improvements that Ed referred to in the earliest part of this pitch. The community has been showing great interest and support for our strategic approach to bringing NASA technology to demonstration, and we are very excited about this opportunity to deliver tangible benefits for NextGen. So with that introduction and sense of where we're going in air traffic management, let me just switch gears. I want to turn back to Ed, who's going to speak about solving aviation challenges through elements of his integrated research program.
Thanks, John. Another challenge under the What's Next construct is that aeronautics is addressing the impact of aviation on our environment. NASA Aeronautics is addressing this challenge on 3 fronts, as shown on the next slide. The first is fuel efficiency. In 2008, U.S. major commercial carriers burned almost 20 billion gallons of jet fuel. The Department of Defense used another 4.6 billion gallons of jet fuel. At an average price of around $3 a gallon, this cost was over $70 billion. So our goal is a 50% reduction in aircraft fuel burn, which of course doubles the fuel efficiency and makes a significant impact to the cost or to the total operating cost that's associated with fuel. The second area has to do with emissions. 40 out of the 50 top U.S. airports are in non-attainment areas, or areas that do not meet the EPA local air quality standards for particulate matter and ozone. The fuel consumed by U.S. commercial carriers we just talked about, and the DoD releases more than 250 million tons of CO2 into our atmosphere each year. So our goal here is a reduction for landing and takeoff emissions of a 75% reduction in those emissions. And the third area is noise. Aircraft noise continues to be regarded as the most significant hindrance to our national airspace systems capacity expansion and growth. An example of this is when the FAA attempted to reconfigure the New York airspace. It resulted in 14 lawsuits being filed against the FAA because of noise issues. Since 1980, the FAA has invested over $5 billion in various airport noise reduction programs. Our goal here is to reduce the nuisance community noise by 5/6 around airports and reduce by 2/3 the area that noise is actually over. And from an integrated systems perspective, we're aiming at meeting these goals simultaneously. That is, the technologies that we're working will work together to simultaneously meet the fuel efficiency, the emission, and the noise goals. In addition, we're working at and assessing the fleet-wide impact as well. So that is not just a single aircraft, but assessing the nation's fleet that's made up of older vehicles, newer vehicles that we know that are coming into service, vehicles with retrofitted technology, as well as totally new configurations. Now the next slide shows how we're organizing this work. It's around 3 areas: airframe technologies, propulsion technologies, and vehicle systems integration. And I'll briefly discuss each of these. Under airframe technologies, the first area is drag reduction. Here we want to overcome some of the practical barriers of cruise drag reduction by integrating technologies. An example of this is laminar flow control. We know we have some critical barriers to the practical application of laminar flow, such as surface roughness, manufacturing, and contamination. And so we're working all these areas. The second area is flight dynamics and control. That is evaluating the performance, the stability, and control for advanced configurations through developing new flight control algorithms, through various kinds of ground and flight testing, and prediction methodologies for control effectors and propulsor combinations. Here we're conducting wind tunnel tests and flight experiments that demonstrate flight control and handling qualities. The third area is airframe noise reduction. Now this is the airframe, not the propulsion system, the noise reduction. Here we're looking to design quiet flaps and landing gear that don't have any performance or weight penalties. We're using aeroacoustic methodologies and high-fidelity wind tunnel measurements to do this. Then we're validating this work with flight tests. The fourth area under airframe technologies is lightweight structures. Many of you are familiar with composites, and we have composites actually flying on aircraft today. Now, they're primarily used as what we call black aluminum. That is, the underlying structure is still the same. And so we're looking to achieve additional weight reduction through lightweight, damage-tolerant, stitched composite structures. This has the potential for an additional 10% weight reduction and may enable entirely new classes of vehicles to be developed. We're going to run a video that's an excerpt of an interview with Dawn Jegley, one of our senior research scientists, where she explains some of the technologies and the benefits that are associated with stitch composite concept known as Perseus. That stands for Protruded Rod, Stitch Efficient, Unicized Structure. So if you could run the video.
Well, Perseus stands for Protruded Rod Stitched Efficient Unitized Structure.
Okay.
What that means is that we have a large panel, and this is a Perseus panel.
Right.
And if you look real close in here, you can see stitches. It's all held together by stitches. And what you'll notice when you look at this panel, rather than a normal aircraft panel, is you don't see any fasteners. In a normal airplane, you've got rivets all over the place holding every part together. In this case, we have no rivets.
Right.
Everything's held together by stitches.
Okay.
Now, composite materials have been around for a long time. We at NASA have been working with them for 40 years. Industry's working with them, and they're now getting out into real aircraft structures.
Gotcha.
But what's different about Perseus is a couple things. First of all is the stitching. Composite materials, composite structures are put together using layers of graphite epoxy or carbon epoxy materials that's all built up into whatever configuration you're looking for. With Perseus, what we're trying to do is build very large unitized structures. So we can get away from all those fasteners by putting in the stitches and by making very large parts. So composites are useful. Composites are good because they're lighter weight than aluminum.
So the next area I'd like to discuss is related to propulsion technologies, or the engines that go on these aircraft. And hopefully I'm going to be able to do this without going all techno geek on you, and as we get into some of this kind of complex subject matter. But we've broken that work down into three areas. The first is low NOx, fuel flexible combustor system. And there we're using various new structures, new materials, and innovative ways to mix the fuel and the air together for combustion efficiency and active combustor control. We're also looking at low noise, high efficiency propulsion systems. So when I say that, think about the engine fan. Here we're working technologies to reduce the fuel burn as well as the airport and community noise. During this work, we'll be establishing a very robust database to do trade studies between fuel burn and noise reduction to look at the differences between the two and those trade-offs. And then the third area is high pressure ratio, high temperature core. So think of the compressor on the engine in here. So we'll be doing systems level test validations of higher overall pressure ratio compressor technologies, new materials for high pressure turbine vane applications. And we have to marry the airframe and the propulsion system together. So they come together in what we call vehicle systems integration. One of the areas that we're looking at here has to do with how we do that efficiently. So how we put the engine on the aircraft with zero interference drag penalty. So you do that without incurring additional drag. Another area that we're working under vehicle systems has to do with propulsion airframe aeroacoustics. Now that's a mouthful, but basically it's looking at ways to marry these two systems, the propulsion system and the airframe together, couple these with the potential of bringing those together without additional noise effects. So the aeroacoustics part of this. Pretty complicated. We've got a clip that another one of our senior research scientists, Russ Thomas, will be explaining some of this work done in propulsion technologies and vehicles technologies together. And this will focus on some of the unique ground testing that we're doing and the ground-based experimentation that we're doing. So could we run that clip?
Will this work on commercial aircraft as well, or other aircraft?
Yes, it's very relevant to other types of aircraft. Again, what we're looking at here is the effects, the aeroacoustic effects of integrating propulsion and aircraft. And at NASA we call that propulsion airframe aeroacoustics. It's very relevant to any type of aircraft that you put together because you have to integrate engine and airframe to come up with the aircraft system.
What is so special about this facility?
It's the Boeing Company's low-speed aeroacoustic facility. And NASA is working with Boeing on this experiment. It's an aeroacoustic wind tunnel, which means it's specially designed to be able to measure noise properly for aircraft applications. So you can see it's a large chamber that's got soundproofing material. It has a large wind tunnel, 9 feet by 12 feet. And we can put the airframe and the propulsion source here in the wind tunnel, and it's got all the right instrumentation that we need to measure sound properly. We've got it all here. And one more important aspect is that this airframe can move relative to the propulsion source, so we can investigate all those different combinations of the engine and airframe together.
So there you can get some sense of the work that we're doing to understand the placement of the propulsion system on the airframe. We're also using systems analysis, using this to support decision making and guide our portfolios by identifying and prioritizing the various technologies and configurations that we're working that are capable of achieving these the performance goals that we've talked about. And finally, we're working and looking at advanced vehicle concepts, so new vehicles, to identify and create a robust set of configurations and technologies to enable the simultaneous achievement of these performance goals. One of the key elements that we're using here is part of a NASA research announcement studies that were competitively awarded and are being performed at Lockheed Martin, Northrop Grumman, and at Boeing. In these studies, the contract awardees are providing detailed analysis and testing and assessment programs of their preferred subsonic transport configurations that they feel will simultaneously meet these goals that we've been discussing this morning. So what we'd like to do is conclude this part of the challenge discussion with a video clip of some ground and flight testing of a scaled model of an X-48B, a remotely piloted aircraft. The video will open with a very short shot of some flow visualization that was taken during some low-speed wind tunnel testing at NASA Langley. Then we'll transition to Dryden Flight Research Center and take you through a flight as part of the Phase 1 flight test campaign. Now, this flight campaign is a joint undertaking between NASA, the Department of Defense, and Boeing. And the model that you'll see in this video was actually built by Cranfield Aerospace. So if we could run the clip. So this is the first part. This is doing some very simple flow visualization up at fairly high angles of attack to see how the aircraft performs and how the flow goes over the upper part of the wing. Now we're transitioning out to Dryden. This shows the rollout of the vehicle. This vehicle is 21 feet, has a 21-foot wingspan and weighs close to 400 pounds empty and about 525 pounds full of fuel. You see the ground support station here. This is actually the pilot. And you see the view out of the nose camera. You can see on his screen there. This vehicle is built from composite materials.
Skyway 48 Tower.
Can hear some of the researchers and the discussion going on in the background of hitting the test points. It's about an 8.5% scale model of what could be a 240-foot span conceptual design.
7 traffic is departure roll.
1.01 Matt.
The three engines provide around 160 pounds of thrust, can fly about 140 miles an hour, has a service ceiling, I think, of around 10,000 feet. During most of the flight testing, we got up to around 7,500 feet.
Go 77, only 22 right, wind calm, cleared option.
The first flight of this vehicle was in July of 2007. Lasted around 30 minutes. We finished up the flight testing in March of 2010 for this Phase 1. You can see it. I mean, it looks and performs very much like a real aircraft there. Here you can see it coming in for a landing out of Dryden, touchdown. So right now we're reconfiguring the vehicle, removing the three engines, replacing those with two engines, which will increase our actual flight time and data acquisition time, give us a little higher performance, and moving the vertical aerodynamic surfaces inboard for a little more noise shielding. So this will give us a noise benefit as well. We hope to start that additional testing next year. So with that concludes the environmental portion of the challenge that we wanted to discuss. So I'm going to kick it back over to John for some concluding remarks.
Thanks, Ed. So what's next for NASA Aeronautics? I think Ed and I have spent a few minutes describing the national agenda that we subscribe to and have been working to help build and satisfy. You heard about the global complexities of this air transportation system and the aircraft that fly within it and our efforts in trying to improve that, make that better. the technical challenges that make that difficult and a very challenging and complex problem. Talked about our portfolio of R&D programs and the missions that they achieve. And we also took some time to describe a couple of the exciting initiatives that we believe can change the future of aviation and make an impact on this next generation air transportation system. So as kind of a final wrap up here, we hope that now perhaps you two can share some of that excitement that that we feel as we embark on our overall mission, our agenda, and looking to create aeronautics breakthroughs for the future. So with that, I believe we now have time for some questions. Beth, would you like to?
Right. Thank you,
take
Ed and
that?
John. We do have time for questions. If you'll wait for the microphone and give us your name and affiliation, that would be great. Anyone with a question right here?
Sure. Pete Crow, St. Harbor Productions. I've got a series of questions about, first of all, what's the relationship between the FAA and NASA, and if you are also putting DoD in this mix, duties, responsibilities, and so forth, between what you're doing and both of you gentlemen?
Okay, let me kick off, and then Ed can provide his perspective as well. From the perspective of the transition to next gen, there is an organization we didn't mention I think specifically, but the Joint Planning and Development Office, which is a collection of federal partners that are looking to help plan the form, the concept of operations, and an actual work plan to enable transition to that new system, next gen. As part of that, Department of Transportation, FAA, DoD, DHS, NASA, Department of Commerce, and OSTP. So from the perspective of coordinating our overall national objectives and agenda, that's been a very productive relationship. In the program that I oversee, the Airspace Systems Program with the Air Transportation Management Technologies, we have some very specific relationships with the FAA that we call research transition teams, whereby we look to bring some of our researchers together with FAA stakeholders at earliest stages around particular areas of our technology development in order to make sure that they know what's coming, what the maturity is, and how it has the opportunity to fit into their overall roadmap and implementation plans. So we have a variety of interactions and connections. We've been doing many of these things for a number of years, and we think that we've got a robust way to make sure that our work has value and return and has a transition path into the system. Sorry, Ed, if you wanted to mention other.
Yeah, another way that we're working with the FAA is to ensure that the technologies and the concepts that we're working at a research level are certifiable, so that we make sure that eventually that they can be actually integrated into a configuration. We do that on a lot of different fronts. We work very closely with the partners. An example of this is we just kicked off, the FAA just kicked off a aviation rulemaking council that is focused on the integration of unmanned aircraft into the national airspace system. This is made up of federal partners, so government agencies, as well as industry partners, both from particular industries as well as industry associations, looking at the various barriers, the various issues that need to be addressed. And so that will help guide our research in this area, as well as making sure that there's not any unnecessary duplication of effort among the federal partners that are working these areas. So our association with the FAA, we work with them very closely, from a research perspective, from a rulemaking perspective, a certification perspective. So we're working very closely together. It's really a hand-in-glove relationship.
All right. Other questions?
I'm Jim Siegel. I'm with the Celebration Independent newspaper. Celebration is Disney's planned community outside Orlando. I have a question about vehicle configuration. It seems to me that from my perspective as an air traveler, that the last significant change that occurred in vehicle configuration, aircraft configuration, was the Concorde, supersonic flight, and so on. I think that might have been in the 80s, I'm not sure. But in any case, the Concorde has just gone out of use. So it seems to me as an air traveler that there hasn't been much advancement in terms of vehicle configuration in the last couple of decades anyway. What do you think is responsible for that?
So I can give you a little anecdote relative to that. Back in the 90s, NASA was working a program called Advanced Subsonic Transports. And I remember sitting in the Director of Engineering's office at a major aircraft manufacturer and talking about this really cool high-lift system that we were working and how it worked and how it increased the stall margins of the aircraft and things like that, and that we were working to reduce the risk associated with that. And he looked me right in the eye and he said, "We don't take any risk on any of our configurations." And when they launch a new configuration, they're putting the entire company at risk when they do that. And so they're going to do this in a very, very safe manner, making sure that there are no technology risks associated with the work that they're doing. So that's why we're working closely with them now, with these manufacturers, in their advanced configurations and the work that they're doing to develop the advanced configurations, to make sure that we're addressing those risks up front and making sure that we're doing that in a way that they accept, not just in NASA's way, but in a way that they understand and they can accept the data and understand the data that they're working with. So that's why we still see tube and wing aircraft. It's just a very risky, from an economic standpoint, a very risky undertaking to launch something new. What you see is often new technologies and new configurations first being adopted by the Department of Defense, because they will often have a less risk-averse posture and be able to adopt some of those technologies. So when you think about supercritical wings, when you think about area ruling, some of the innovations in engines, we first saw those in DoD aircraft.
And another brief expansion on Ed's point, from the integration of new aircraft into the air transportation system, it's critical to make sure that any new flight concepts, vehicle concepts, can actually operate effectively for the air carriers that would be buying these aircraft, in the current system. So from a supersonic perspective or a very high-speed perspective, if you're taking these high-performance aircraft and having to stick them in flight paths and trajectories behind slower aircraft, there is no business case for a carrier to buy that aircraft because the system does not allow them to take advantage of its capabilities. So we need to make sure that all of those things are incorporated in a national decision to consider aviation advancements, because, again, it all has to work together. So just additional perspective.
All right. Go ahead.
Jim Siegel again from the Celebration Independent newspaper. I have a question about the air traffic control system. You were talking a little bit about that, and about the new system called ADSB. Okay, so every once in a while I'll see stories or information that comes out about the nature of the current air traffic control system. Some critics have said it's kind of antiquated, needs to be updated. So is ADSB kind of the next step in modernizing the air transportation system, or are there kind of steps in between that? And when do you think that ADSB would be fully implemented in the United States, a satellite-based system as opposed to the radar-based system that we have today?
The FAA certainly considers ADSB to be a critical next step to enable next-gen, so much so that they have a subscription mandate, if you will, or an equipage mandate in 2020 for carriers to have certain ADSB capability installed on their aircraft. The key element, I believe, is that it provides it gets away from some of the fixed-based surveillance infrastructure that we have now, again, had since the 50s with radar. It improves the performance of that. It also, because we are bringing elements of this technology and our ability to surveil positions of aircraft, some of that capability is actually done on the flight deck, of these aircraft. They can self-separate. it enhances a scalability to the system, implying that you come up with a new aircraft and you're bringing some of the necessary surveillance infrastructure with you in order to be able to safely navigate the system. So it has many, many benefits. I know FAA and that the Joint Planning Development Office consider that to be a critical first step, but next gen is very, very complex, and this new system we're going to, there is no one thing that we can say incorporates all of next gen, nor is there one big system that you develop and throw the switch as you transition from old to new. There are going to be a series of steps that we're going to take in implementing capability. ADS-B is going to be one of them. Other elements of data sharing with net-enabled information exchanges are going to be another key part, but certainly ADS-B is very, very important. And Ed, do you have a?
Yeah, John mentioned the ADS-B, and the first step of this is ADS-B out, where the aircraft will actually be broadcasting their position. So if you think about how a radar works, you know, in the time that it takes to make a radar sweep, that a high-performance aircraft can maybe travel a mile and a half. So that requires a lot of separation because you don't know exactly where those aircraft are. So with ADS-B, there'll be, even for the controller, he'll have a much more precise location of the aircraft. So then as the demand on the system expands, there are more aircraft in the air, then it gives you that scalability that John alluded to, or that's one of the elements of the scalability, being able to have more aircraft safely in a given area of airspace without these large buffers that we have to have right now with the radar-based system.
Okay, we've got time for maybe one more.
Pete Crow again. What roles do you foresee that the unmanned aircraft will ultimately be performing over the American airspace?
Well, I personally think it's going to change our society. But that's my personal bias. But let's start with some simple things. So an acquaintance of mine was actually associated with an air taxi service down here in Florida. And they were flying 4-place jets, and it was, you know, taxi on demand. So you call them up if you wanted to fly from Orlando to Tampa at 1:15 this afternoon, they could do that for you. However, it was a commercial operation, so you had to have a pilot and a co-pilot. Now, if you had 3 passengers, they had to send 2 jets. And that kind of ate into some of their profits. So I certainly don't totally understand their business model, but it had an effect. So one of the first things we may be able to see at some level is perhaps the ability to have a virtual co-pilot. So that would be a very simple thing to do. The technology is there. We'll probably see cargo that is carried in unmanned vehicles. And that would be a fairly straightforward, easy thing to do. The technology is there. We have to prove the technology, make sure that it's safe. And then from my perspective, I believe the sky's the limit. I mean, it's really going to change the way that we look at air travel, that we look at air transportation, and the effect that it has on our culture and on our economy. I mean, right now the Department of Defense is using aircraft in the Middle East. They're being piloted with operators and pilots that are in Nevada. And they're doing this very safely. Of course, they own the airspace. It's not a heterogeneous airspace that you have to mix unmanned and manned vehicles, but it's being done. So the technology is there. It's up to us to prove to the American public and to the rule makers relative to the airspace and those who are stewards of our airspace that this is a safe thing to do and that we can do that without impacting the safety of the national airspace system.
All right, we're out of time. We'll have to call it a briefing. It's been a pleasure sharing aeronautics with you today. Thank you for being here and thank you for watching.